Good afternoon, everybody. It's both a great honor and a real pleasure for me to welcome Karniadakis today for this, what promises to be a particularly inspiring seminar. I have known George for a long time, ever since we met back in 1986, as I said this morning, while I was visiting Anthony Padera at MIT. At the time, George was completing his PhD under the supervision of Tony Patera and Loris Jacques-Louis, working on spectral element method. He later continued his career in Princeton, Caltech, and quickly joined the Division of Applied Math at Brown University, where he has been a major force ever since. Over the years, Professor Karniadakis has received numerous honors recognizing his depth and impact on his work. Many fellowships and prizes, such as the prestigious Science ACM Prize in Computational Sciences and Engineering and the Kingsley Odell Medal Prize, voting for outstanding contribution to stochastic differential equations. His contribution spans applied mathematics, computational physics, and more recently, scientific machine learning, especially through his works on beams, fields in which he has been internationally influential. His talk today, from physics-informed machine learning to physics-informed machine intelligence, invites us to reflect on a profound shift in the relationships between artificial intelligence and physical modeling. The aim is thus no longer to just learn individual solutions, it is also to learn operators, governing laws, and entire behavior. In short, to move beyond learning toward intelligence informed by physics. Through developments such as deep operator network, digital twins, and video-inspired architecture, Professor Karniadakis is offering us a glimpse into a new generation of scientific AI, one that is faster, more robust, and more autonomous. Without further ado, I'd like to welcome Professor Jacques-Louis.
Thank you, everyone. In the last 15 plus years, professional science and engineering, we have this paradigm of pretending that we know all the governing equations for what we want to study, and then we have some small data. Typically, the data will be the initial probability, we only assume, and then we develop methods to forecast the dynamical systems, let's say, about the future. However, in real applications, and that's what I have here, the three bundles on just described on the left, small data. In real application, we have some systems which are complex systems, or systems that we know the governing equations, but we simply cannot solve them at the scale that we want. For example, thermal flow, which is all open from classical physics. So in that case, we have physics, some physics, partial physics. We have some data. The data is not conveniently located where we need them. The data could be asynchronous, could be sparse, some gaps involved. So the middle bucket represents the real situation. And then there's also digital twins with complex systems of systems, certainly in social dynamics. It's a case where we have no physics at all, and we need lots of data to deal with. So I'm talking about how we change the paradigm from the classical paradigm to going into data learning or hybrid models. But moreover, here in the top, we have a pattern. That's a pattern that we introduced of physics informed machine learning. We did that 10 years ago. From physics informed machine learning, which was one of the big centers that are directed for the development of energy in the United States. Now, in the era of general intelligence, the question is, where will scientific computing go with this general intelligence, reasoning, causal inference, and so on? But before I go to my talk, I want to talk about Professor Lyon's. This seminar dedicated to it. And in 1991, 100 years from the rebirth of the Olympic Games, and this Greek, so I have to thank the French people who actually restarted the modern Olympics. Professor Lyon's was in Athens to give the lecture with the title, "The Computer is the New Daedalus." Now, in Greek mythology, Daedalus is sort of the Da Vinci of mythology, because Daedalus was an artist, he was an engineer, And this was the scientific Olympiad that arts and science were together. But as I have highlighted here, in his talk in 1991, he made the analogy between complexity and labyrinth, which was associated, of course, with in-house civilization. And then he made the analogy of what you see in the sketch of Icarus and Daedalus. Daedalus built this robotic bird, or his human bird. So he was talking prophetically about a concept like artificial intelligence as precursor to robotics and artificial intelligence. That's why the title of his computer is the new Daedalus. He talked about that in 1991, and if you look at the history of AI, 1991 is sort of the big deep winter of AI. People were not interested in AI. We experienced, as you can see, a couple of AI winters, until, of course, early 2000, with the invention of GPUs. You can see here a sort of monotonic increase in AI in general. Here, just for those of you who are not in the field at all, I have highlighted sort of the birth of scientific machine learning, which is the scientific computing and machine learning together. And although I don't popularize scientific machine learning, and I coined the term, as you can see, in 2019, I hosted at Brown the scientific machine learning first workshop. And the paper that defined this area was in 2017, but I have highlighted in 1994, there was an attempt by some polymer scientists to use neural networks, neural networks, to solve for the first time the PDs using neural networks. I also had a couple of introductory slides to talk about why neural networks are good for scientific computing. And just looking at the inverse function approximation here, equation that says theorem 1, y equals the sum of this wi's and sigma argument with linear argument. If you look at the sketch, x is the input, y is the output. We approximate the single layer, a shallow neural network. We approximate the function, and you can see wi2. Well, yeah, W2 are the linear weights because we don't apply the regression problem. We don't apply nonlinear activation functions on the last layer, which is linear. So with all that together, you can write y basically approximating the function, and then the linear sum of the non-coefficient signs are made. Is that basic is a nonlinear activation function that takes as an argument the linear input. So in that form, it's not very different from what we are familiar with the classical methods. In fact, I may, of course, this issue here, where I take a deep neural network, and if you go from left to right, the inputs x1, x2, the scalar output u, you can write the neural network, and theta are the parameters of the neural network that define the biases and the weights. You can write again as a linear sum of some unknown coefficients. These are the weights of the last layer times the basis. Now, what is the basis? Before, the basis was simply the activation of the one external layer. Now the basis Q1, Q2, Q3 are really the last layer, the last hidden layer, the last nonlinear layer is the basis. So in that form, again, this looks pretty much like a finite element or a spectral method, except the basis phi is not a priori chosen. They're not ad hoc polynomials. This is an adaptive basis that depends on the data. So I use this argument to argue that indeed neural networks is a good candidate for representing functions, and later I will tell you about functionals and operators. In fact, this analogy can be made exactly if you use a ReLU activation function. I have a sketch of ReLU, it's a round particle. You can show a total equivalence between a shallow neural network and the linear finite element, just by constructing the hat functions, which are the test functions of the linear finite elements. You can introduce that basis using the ReLU activation function. Therefore, the linear finite element space, one dimension is the subspace of the shallow neural network. That analogy valid in high dimensions, anyone know the answer? In TIS, but you have to go to deep neural networks. So there's actually theory in that. But for 2D and 3D, you can prove, I do that in my class. You can prove that again for deep neural networks, the analogy is exact between linear finite elements and real neural networks. So there's a good reason that gives us some confidence that we can introduce things that we are familiar in calculable with, namely linear finite elements. So what is a pin? A pin is a method that tries to abandon some of the bottlenecks of the classical methods. For example, building a grid. I've been around for a long time, and I know I work a lot with industry. So I know it takes a lot of time, let's say, to create a mesh of a flow around an airplane, an Airbus airplane. So it takes months, maybe years. So we want to remove that. We want to have truly meshless methods. We also want to have exact operators. So instead of approximating differential operators on the grid, on the lattice, we want them to be exact. That can be done with automatic differentiation using computational graphs, using neural networks. So if we take a neural network X1 and X2, here we pretend we solve an elasticity problem. U1 and U2 will be the output from left to right, beta output. If I have enough data and we do an experiment 10,000 times, then you have measurements. So then if I compute the H-square error, so I was practically mentioning that avoid some bottlenecks of the classical method. So we want to remove the tyranny of mergeful operators. We want to have exact operators, and we want to have fun data, but not a lot of data. For example, for data-driven methods, just to compute the H-square error, the mismatch between the data and what you're predicting, you need 10,000 measurements for a single experiment. Okay, we get, let's say, 10% error. Or here instead of saying you may or may not have some measurements, so you don't need to have any measurement, but in case you have some measurement, just to give you an example, if you do any of the classical methods and I give you one measurement, 1 point measurement, you don't know what to do with it. Here it's not the problem because we can go from 0 measurement, 1 measurement, thousands of measurements, as you will see. So we have this operator, then the operators satisfies on conservation laws. So then we can basically use the conservation laws, the physics, compute the physics at certain points randomly in space-time. That's what the panel on the left showed. Random points in space-time. We compute the conservation law there, and in fact, that's how we inform, using physics, produce data. We produce data directly from physics. So there's a very nice and seamless blending of data and physics. We then can put the total loss function will be the data MSCU and then SEF. These are basically the residuals that you're trying to minimize at these random points. I have an example here of a radio situation. This is something that we teach in undergraduate or graduate class. It takes about 6 months to get to the point where we get the solution. Here I show you that when it comes data in the XT domain, you can see that I don't have boundary conditions everywhere. So even for this very simple problem, I cannot solve it with any of the existing methods, unless you interpolate linearly, which is not what they're writing in the and boundaries. So here, with one, this is TensorFlow, it's a model slide. We define the neural network, and then we define the residual on the conservation law. The F is the residual by just taking the derivatives in time, space, and then 10 minutes later, high school student, given this solution. And I'm telling you a story of a high school student who actually solved this. In fact, I wrote a paper with him. It's out in 1919. So I'd like to tell you, we took several decades to build the theory. Our group and other groups that started working on the convergence and generalization of these types of pins. Here we're dealing with this paper, we're dealing with parabolic, linear parabolic and elliptic PDEs. We also can compute their estimates, both for the discrete case where you have a finite number of random points, also the discrete case where you use the familiar concept of stability, and also consistency and stability, but in high dimension, you have to deal with paradigmatic complexity and find a priori and a posteriori error estimates. So these have been done before. So I just want to give you some highlights of the past, but I also want to tell you about a new generation of, since we first wrote the paper in 2017. I just want to tell you about the paper. When we wrote the paper in 2017, we got part 1, part 2, and we submit the paper for Proceedings of Royal Society, and the paper was rejected. And the reviewers were arguing that this method was very simple. So I was actually very, very upset, but also happy to hear that usually they accuse me of the opposite, that all my methods are complex, somebody can use them. Then going back all the way to spectral element. So, but this one was simple to use, but they didn't like it. So there were, of course, other flaws of the method. But here I want to show you a result that we get for the Verga situation. What they're showing is already this green line. Is that error versus the number of iteration converges. We get accuracy and the minus 2 and accuracy. Depends on how many points you use. But where we are now using new optimization methods, which just emerged, we can go to this line, which is down to the last line using this scale Broyden method. And I'm talking about that. Now, the big bottleneck in neural network is actually the optimization, because you are trying to solve a optimization problem of a non-linear, non-complex function in millions of dimensions. Trillions, if you're doing ChatGPT, they have to solve this problem in trillions of dimensions, and it's a non-complex problem. How do you deal with it? So these methods starting with Broyden, the BFGS methods, and so on, they don't compute the Hessian as a second order methods. So just like Newton method was a Newton method, they don't compute the Hessian, but the inverse Hessian is given Hessian by the ceremony HK plus 1 and equal to HK plus the still right 1 terms. Now, there's a series of papers by Alabadi in the 90s of optimization that they introduced this scaling factor sigma K, which you can see that produce explicit expressions. You can do that, or you can actually make that the one hyperparameter, especially for multi-scale problems. This helps a lot. So revisiting some of the problems that we did before, like Ramontos-Vadzinski was one of the problems we couldn't solve because we get here very quickly. Now we can solve it with very high accuracy. And compare here ours, the subscale Broyden, and versus solve. So this is one of the latest and the greatest products of Google. With the list in their library, the optimization library. Then you can see we built it by orders of magnitude, just with a one single constant, the subscale constant. I would know what was solved based on another, and Google, big state-of-the-art solver. You know the name of the previous one for solve was called shampoo. So you went from shampoo, but and then you went from shampoo there. So okay, so I want to tell you now how neural networks learn. Something that just bits and pieces of information of bottleneck theory. But let's say you are inside the neural network and examine layer by layer what happens. In the process, I also want to tell you about this weights that turn out to be very important. For example, we have weights. You look at the loss functions that fixed global multiplier. So the data, we have the boundary conditions, and we have the PD, and you have these constants in front, like Lagrange multipliers, that you can choose manually, or you can, there's theory that you can use to find it. Then I'm going to tell you something more complex on that. I want to look at the PD. I want to assign an attention weight to every one of these points, which are sampling points. They can call them residual points. You can call them collocation points. You can call them sampling points. So every one of them will have a lambda I. Now you're going to have millions of them, so you maybe say, oh, I will introduce millions of hyperparameters. How do you find them? I'll tell you how to find them, but there was some work by some people from Texas A&M where they did some adversarial training, which means that you will solve the minimax problem, try to minimize the loss function, but then you want to maximize with respect to this lambda I by intermediate. So these are called attention weights, and they're based on in this work by SSLM was based on gradients, which of course very expensive, especially if you have noisy case. So what I'm going to show you that actually you can compute this lambda rates from the residuals at each point that you have anyway. It's a trivial computation. And also I will tell you, when are you done? Anybody here knows when do we exit? We say we train the neural network. How do you know that you are done? Anybody knows? You typically go and ask your graduate student, and then I double check. I also ask my postdoc. So this way it happens. But there's actually a rigorous theory to tell you when are we done? Are we there yet? Are we converged? Well, that's one big question. So I will use these weights to tell you exactly how we're converging. I think I have a movie that I can play. So you can see the weights here as along the size. When I start, thought we have the Kellogg's equation. It had a certain pattern they call that we can see here on the right. But I start the iterations, so I'm monitoring these weights, and then when I uniformize all these weights to random numbers, then I stop. Because if the residuals are uniform and random, then there's no gradient, so the gradients of that random are therefore you stop. So that's really a true criteria. In the process, I want to define something else. Here I'll play the movie again. I want you to pay attention to the middle panel at the bottom that says, not sorry if I have the pointer, mean SNR with the signal to noise ratio. So what I do, I take the gradient of the loss and I break it up into a mean plus a missed fluctuation. Okay, I'm going to monitor this because there's a very interesting theory going back to Talib Tishby, passed away a couple of years ago, but he, in the 90s, in statistical physics, he introduced information about length theory here, and basically he realized that the mean gradients go to zero, and that's where all the students finish. They say, oh, we're done because now my loss function will reach a plateau. That's actually not good enough because you just fit the data, but you didn't learn anything. The learning process starts exactly when the mean gradient becomes zero. And if you look at the fluctuation of the gradient, at that point where the mean gradient goes to zero, the fluctuations from zero become order one. You have a stochastic gradient descent and so on. Now, why is that important? Because if the fluctuations are large, you're very close to minimum, but now you also go around that minimum. You go in the neighborhood. So if you don't do that, then you're not going to learn anything else. You're not going to just follow the data, but the idea is to forget the data. Rather than sort of the information about the theory. But if you look at the ratio of the mean gradient to the fluctuation, which is this here meaning SNR, we will see that follows the deterministic path, and then at some point, the number of iterations on the horizontal like this becomes very chaotic, as you can see. But the single number will determine everything, and I won't tell you about that. So the information about the theory suggests that there's a phase transition. There's a phase transition between the fitting data as another variables and the training process. So previously they divided things like fitting and fusion, where you've seen the stochastic fluctuation that they talked about. But actually there is this transition period that's also very important. We're going to see what happens. That single number, SNR, the single motivation, defines all these stages of learning. So most of the people stay in the fitting regime. That's not enough. You're not going to learn anything. You might as well do these squares and you're done. You have to go through the transition, but that's not enough. Again, you see here SNR is one, which means we have a balance of the fluctuations with the mean gradient, the direction where you have to go next. But here we see that the fluctuations are large, and zero regime, that's why we go outline. And then finally, with that one, from the fluctuations, we now have to turn directions where we choose the neighborhood. In other words, it's like if I send you to Times Square in New York City and you go only there in one shop in the Hard Rock Cafe and nothing else, you're not going to learn anything else. If you wander around Times Square, you learn a lot of things. So lots of things are happening. The same thing, you're in Lost Landscape, you don't just go to the minimum, you sort of go around and around and around, and that's what we get. In fact, we apply this to many different flows here, other alcohol, gateway awareness, probably taught without these lambdas and with lambdas that follow the two, and we can see that they all look the same, pretty much the same, just like in the sketch like that. This is just a little introduction to tissue, a little bit, but I know at least in my group, nobody wants to go through that phase, the transition phase and the fusion phase, because let's say you train for 10,000 epochs to go to the minimum, and then there's another 30,000 epochs. Nobody wants to do that. With my students, don't want to do that. But that's where you're actually learning. So people are complaining about generalization, and you have to go there for learning. Yeah. Another highlight here is I want to talk about how pins can be the curse of dimensionality. And here I'm using a sort of Olympic equation, high dimension D. Now, I want you to think of D not just as 10 or 20, but 1,000, 10,000, 100,000, even 300,000. So if you see how you compute the gradient, I have the red part and I have the blue part. The red part depends on theta, the blue part does not depend on theta. They have to do this in computation. Now, the question is, if you have a lot of dimensions, you have a lot of data, you won't even bring into a GPU. So you have first of all, you have to do it in parallel, but I don't want to do it in parallel. I want to build the curse of dimensionality, and I want to do it on a single GPU. So what I do, I introduce the concept of stochastic dimensional gradient descent. So for those of you who know how your network works, when we deal with points, we don't deal with all the points in at once. We don't deal with the whole batch. We call it mini batch. We put the spotlight on this number of points, this number of points, this number of points, until we complete the whole icon. And then again and again and again. Is that clear? I divide my domain, subdomain, and then I look at different points. The same thing if you have high dimensions. You have 1,000 dimensions, you break it up into 10 dimensions, you go 100 times around, you cover all dimensions. And then you repeat again and again. Now, when this method works with the stochastic gradient descent, in our sense is yes. So we produce here two algorithms. You can see what this is stochastic dimensional gradient descent is. Just like gradient descent, except I don't use the full dimensionality. In every epoch, every iteration, I use a subset, and then I cover the entire set, and then I go again and again. What I have to show is that this SPTP is unbiased. It's unbiased, then we can prove conversions. I'll take things more like then we also show that the mean matching in terms of points in the equivalent, which is building the variance, just like the dimension rotation is the same thing as point rotation. And then down here, we have an error estimate that shows that depending on the learning rate, sample stated with boundary from every moving part. And I want to show you the results, and then you can go and look at the papers. When we get the sample Jacobi-Melton equation, one with optical equation, the vehicle file, and this is the exact solution. You can see the solution is not separable. Here, we use an exact solution. And if I look at dimension, 150 dimensions, there are figures in the literature by White and E and others. As you can see, it takes 38 hours for them, or 12 hours, the state of the art, roughly 210 minutes. Before we go to 100,000 dimensions, not from 250, but 100,000 dimensions, my time is from 10 to 855 minutes, which is just a memory fetching. I totally killed the promise. You can see that none of these other methods can go beyond 1,000 methods space and more than 5 days for 1,000 dimensions. So really is working according to theory and then get pretty good results or arbitrary, not just that Hamilton Jacobi, but time ordinary equations, black holes, line blood equations, and so on. So it's a method that been the case of machine. There are several theories that we have. The theory is some theory on this is missing. So anybody who's interested in this, there is plenty of room for improvement. But we know that really do this on a single GPU, not the. Oh, the other thing is that all the methods using the thermal touch transformation where they do a single trajectory. We saw this for the full field. In other words, thousands of trajectories all at once. So in terms of speed up factor, it's multiplied by about 100,000. All right, I want to also show you a real problem, a fun problem. We did that early on. It was a DARPA problem. DARPA is the defense of internal defense for research. It's the only one that happened on this panel. Yep. But so they had this kind of, there were 12 teams, and they said we have this data, ultrasound data. It's a video, and I don't know if I've seen a tiny crack. Just like sometimes when you fly with the airplanes they always have some tiny cracks up there, not going undetected. And so those of course could be catastrophic, as you know. So the only thing you have is an ultrasound. Can you automate the process of things like zip like that and find out where is the crack and potential? So there were 12 teams, 11 teams said that they didn't have enough data. While I was present, was at Carnegie Mellon University. I instructed my team to use only 10% of the data. So I didn't want to beat them. I want to beat the budget. And what we mean. And the idea is very simple. If I have 10% of the data, I can use the physics for the rest. So here is the case. So let me just go to this slide. Okay, so what if I is a video like this that you see on the left? And that's the ultrasound video. So that you just now something to 10% of it. But what I use is this equation, the way equation from side, and that's what the pin. The pin will go there. Now C is not known because C is constant for a material, it is homogeneous. But the material has cracks already, it's inhomogeneous, how they back because we have seen a factor of again. So C is actually a function. So if I'm determining the function and find the zero contour is exactly the crack. So I know the shape, the orientation, the size, everything. So that's what is shown here. That's what you do. So just in terms of the architecture, with it, this is what the architecture is. When you need a pin architecture that will give you psi for the physics part, and then we need to estimate the unfair C, the speed of sound, which is function. But neural networks, represent functions. So now I have another neural network, here so Y, I do a normalization simultaneously, and I can compute not only C and Y, but I compute also psi at the same time. Psi matches the pattern that is given to me in 10% effect, and then I can naturally get. So anyway, we ended up writing the paper with the people who said that this there's another paper published in 2019 in Science in posing questions like medicine in classical fluids and so on. And you can compute body forces based on flow visualization. I call it hidden fluid mechanics because in hidden Markov chains, you sort of have the observable on auxiliary variables, but you don't have the project variable. Here, we know the passive scalar, but we don't know the velocity and the pressure. So, am I compute the velocity and pressure, therefore I can compute the forces? And the answer is yes. In fact, I asked a postdoc to do this cut out, saying what topic of the pins are the rising. So you see here, this cut out, I have the video, but that's where I have a passive scalar, I know the vector diffusion equation. And then if I match the dye visualization with that, then I know the ways, then I simply sample, because the same neural network is multi-physics problem. I sample the rest, I find the correct answer. I find, although I don't know about algorithms, I don't know radius sums, I don't know all this, because I don't even know with the guide. Okay, so and then my last example, something that we're very excited to show this to Oxford a couple of weeks ago. It was still unpublished. So all our brains, thankfully, are sitting in a block of fluid. It's called the cerebral spinal fluid, which turns out to be as important as the blood. And in fact, more importantly, if you have a headache or hydrocephalus or Alzheimer's, all these neurodegenerative diseases are due to this disorder of this. But it's basically everywhere. CSF, that's where it's produced. So it's like the brain is like a sponge. It's a porous medium. with it. So nobody ever has measured the velocity and pressure inside the brain, especially deep in the brain. That has never been done. And we'll do it here on the live mouse. But guess what we do? We inject the information with a mouse, live mouse, and then we basically we do MRI. This scene stands for deep photograph enhancement. And then we have passive scalar again. And from passive scalar, using Garcia's law, that actually the human brain, we can obtain the velocity, the variability, and so on. We can not with just in the details, but this is where these are the different times that we can see the diffusion of information. And I just wanted to show you that actually you can get a 3D velocity internet deep in the brain everywhere. You can see red spots, high velocity, blue spots are low velocity in the intermediate ones. So for the first time we have a result like that, that will also per region, you can see where the circle width is, the highest velocities and so on. And 5 different ways pretty much be the same. So pins have been huge success in the industry. I work here with the SO and analysis and video. In fact, NVIDIA was the first to adopt it. They changed name 3 times. And now I think they call it physics Nemo. Case Nemo. But so here you see, yes, the CEO of NVIDIA, didn't talk about physics support neural networks. And how did he build it? The old-fashioned way. He hired my boss behind my back. That's how he built it. Now that he built it, didn't talk with his amazing. So he played a lot better than that. Eventually, his assistant called me up and said that it was 2 Christmas ago, Jensen wants to give you a Christmas present. So I was very excited. I thought I would get a bunch of NVIDIA stocks. Then he sent me his favorite whiskey, which was, I looked up his Japanese whiskey, $100. And at that time, one NVIDIA stock was $300. I complained some more, and then finally he sent some NVIDIA hardware. So things are used everywhere. There's a lot of problems, of course, but they're used because they're easy to use and they can on the data. So after all the euphoria, what is the problem? I'll talk about problems. For the rest of my talk, I'll talk about problems. Well, there was this paper from CSAIL from MIT that basically they were saying, okay, this is the red area where we need to declare against this one power, but this is where we cut. So only the rich people like Elon Musk and big boys, some other and so on can afford to train on big neural networks. We know that. Not only that, it's not just the money. At least in Europe, people are interested in having this and the pollution. So this is what our pollution ChatGPT 2, ChatGPT 2, not 4, not computers. But I can see there's a lot of CO2 emissions just from benchmarks. So clearly, if you look at the human brain, the human neuron, human neurons work very, very differently. For example, there's stochasticity. There is event-driven events. The data that comes in are pulses. They're delta functions. They're not continuous strings. And then memory is in situ. We don't go out, bring data to fetching and data and so on. So there is, if you look at it, there was this picture of AlphaGo, and DeepMind are very good in selling their stuff. But they didn't tell anybody how they beat the master as a master, beat them once, only drinking 1 cup of coffee and then chocolate, which is 20 watts, as opposed to 2 megawatts power that they use. And ChatGPT uses 20 megawatts of power. So if you look at the energetics, a human neuron is 1 million times more efficient than that of still neuron. 1 million times. So that, of course, cannot go on forever. So tell me, can we devise new methods which are bio-inspired, just in the sector? Just to differentiate between the dog and the cat, you need 250 watts. And of course, in our brains, we do multitasking and we can spend 0 energy for that. So anyways, I want to advocate the use of spiked neural networks because spikes like this is what's coming to the right. You can see here what's coming to the human brain, the membrane with human neurons, the membranes of the human neurons, and then you're not firing neurons all the time if you don't need it. You only fire neurons when you see a certain pressure, where there's sufficient information that you need to do that. So if you do that, the prognosis or the forecasting is that you can actually have a more slow what the bacteria say that every 2 months the means of computing is doubling. But now it's like neural networks where we'll be able to bring that the slow down and also somehow the value of the energy. So as something in 2019, we published this paper on neural operators. So in PINs or any neural network, every time you change something, you have to retrain, and of course that's the main goal. So here we introduce a higher level of abstraction. We say, if you just change the boundary condition, you need to go back and retrain it. I want to do this for all boundary conditions, but I anticipate this system will be surgical. I want to do this for all Reynolds numbers. I want to do this for all Deborah numbers, for polygons, and so on. So I want to do this for a plurality of instances, not just one instance. And I want to pre-train this just like we train ChatGPT. And then during inference, I want to do it in real time. So what I say is we have, and I show it here, and in analogy between human neuron and this two neural network. So if you see up there, the branches, the dendrites or branches, and then that's the input. That's what we give human neuron tracing. And then down on the other end, then you have a person to show you. Like that's not alone. But on the out here, the yellow, that's the synaptic outwards, and then the cross term is the other. So we have the branch to the left, and then we have the sum on the front where the computation is done. Then I have another neural network on the right, which basically will compute the basis that I talked about earlier. The base is not for the solution, but for the operator itself. And then, so what I have here, automatically, I have functions in and functions out. That's very different from the standard paradigm. The standard neural networks, you have a finite dimensional space map, a finite dimensional space. For example, in NAST mode, so commercial, Saddam China. We're talking about functions as inputs, not data. So we have data in, data out. A function is a neural network, right? Neural network is a function. We don't know. Now I have functions in, functions out, then I have an operator. We're talking about the neural and an operator, that I don't try to discover this operator. So you can see that this is true also for system identification or some different applications. So we proved a theorem for deep neural networks that indeed they go from UTQ on GLQ while the field operator, and I draw from a complex that I will prove that GLQ follows the method of space of here with this down summation. If you look carefully, there are two neural networks, an G and an F. So the branch and the trunk, just like I sketched it. My neural operator works, resembles a human neuron, has zero, and then now based on that, we can build an architecture. If I have a single hidden layer, this is now a more explicit unit expression, and you can see what happens with the U is the input, but it's a function. So you sum U at n points, U of xy, in some sense is a projection for looking at those space, undimensional space. That's in this triangle, seeing the sum of their n, getting the power to n. And then the current where the basis, that's the output space. So we construct a basis to express the operator of in the output. And then we sum them up and we get the one thing. We did theoretical work at Misha, that I did a talk at the hub at that time. So one of the students was there, so he did this for that. So you can see what happens. The encoding, you take the U function, we project it as like a projection now. Then we'll have the approximation of it, the showing the theorem, the universal approximation theorem. And then with the basis, we need to extract, that's an encoding, there's a reconstruction there associated with that. And the paper is long, it's 120 pages, theoretical paper. But there's some interesting practical conclusions that I summarize here. For example, the almost then the best sampling is the random sampling, turns out. Also, we can show that we can beat the curse of dimensionality in the able space. In other words, you can deal with parametric PDEs in many dimensions, not just 10, 12, 13, or 1,000 dimensions in the. How do you exactly train this? It's kind of an issue. We train the trunk and the branch, which can be independent network, but we train them initially together, but it turns out that it's better to train the trunk first with a QR or an SUD, or for normal and the basis so there's no linear degeneracy, and then you can do the branch. So if you do that, now I'm showing you that basis, you can solve some really difficult problems. For example, here we're solving a Riemann problem. The Riemann problem is the Euler equation. You're solving for a high pressure on the left, low pressure on the right, relaxed problem, solved problem, and so on. High-speed aerodynamics are Riemann problem to both the Riemann problem. So here we probably don't link the numbers, but down here to the right, the right pressure to the left pressure is 10 million. Very, very difficult problem for any method. So we want to vary that ratio and see if the neural operator can learn. Turns out, like I showed you, they did a good job, but what I want to show is the basis that the depot net produces. The basis, if you look at B as mode equal to 0, we can see that the basis fits exactly the data. Then if you look at mode 10, look at that mode, that basis. It's like a Fourier series, and then it's like a wavelet local. It's a mixed basis, but this basis is including all the trig. And so if you look at the 120 basis, you can say it's like a Fourier mode, except it keeps the constant state. One of the property spectral method, we cannot represent the constant state sometimes. Right. So it's very important to have integrable durable operators. And I saw that Andrew Stewart and other people came around. They developed this Fourier neural operators that cannot do this. The different type of method they developed examples. Okay, so we're going to do a real application, and we wanted to please Elon Musk, and we want to be on the cover of magazine. So we asked ChatGPT to help us, and help us for this study. We were looking at metamaterials. So we had metamaterials for SpaceX. So Daddy gave us this. See the X? And a little satellite. So what's the problem we're solving? Here we 3D print materials, and we want these random components of materials to give you a certain stretch strain relations. Very difficult problem because you have random materials. So you can see we printed about 20 materials. Some German companies, some German people was to work for a similar problem. The Germans are working out very hard, as you know. They print 1,000 materials. We didn't go more than 20, so we assumed 20 samples, and we trained the network. Now, this is a default vector that has the physics, where there's an equivariance reservation in it. It has to guarantee that invariance and other properties. We don't have time to work through it. But basically, we can produce some anisotropic curves in different directions, express the relationship with correlation of more than 95%. While out of random components, we can even design a material which is anisotropic. You can see all the directions in the same. And we predict, then we ask the other student, the other postdoc, we go to the lab and print this material and so it's a blind comparison. But working with almost done. So I talked about deployment provides a plurality of neural operators, and the branch could be anything. It could be a standard neural network, a graph neural network, a spiking neural network, and the same thing for the planet. Here I color coded everything. A little bit more about spiking neural networks. The major difference is that for artificial neural networks, we assume the nonlinearity. We say, okay, at a lower hyperbolic tangent, this be a sigmoid and so on, or something else. But in spiking neural networks, the equivalence is that basically we follow the membrane, both the membrane law. And you see that we have here the 4 spikes coming in, and only when you exceed a certain threshold, you have this green files when it comes out. Now, what do you save? You save a lot of memory, that save a lot of cost because you don't have lots of data to deal with. The only difficulty is how you encode the information. So the bottleneck currently for spiking neural networks is how to train them. So one approach is to train an artificial neural network, and then during inference, you go with SNN. Why inference? Because training offline, then let's say you have a car or an airplane, then you do the inference on the fly linearly without paying the cost. But they can use. The difficulty is, of course, how to deal with backpropagation, take gradients of delta functions, which are so we more recently we published the paper in Sino the computing on randomized total model gradient estimation, where we don't actually abandon totally the backpropagation. So I'm going to give you some results. This is based on OAC2, which is the only robotic computer chip in US right now by Intel. I'll be a national upside one. So in this case, we're solving the Poisson equation using a default. And you can see I replace the lower one, which is the trunk, with a spiking neural network, but the top one could be injected. This is just demonstrated. So I'm solving Poisson equation with the different right-hand sides. And you can see the solutions here. It's not grading. There's a quadratize. And the reason is it's very difficult to represent the function using spikes. So how it may encode that information is very important. When you have an image, you can do it with brightness, you can do it in the temporal information, and so on. That's like, if you refine it, let's see at the bottom whether we have a different type of encoding that function, then you can do a better job. So again, the question is, we have all these types of machine learning. Can we reduce the cost? And typically one would say, use transfer learning. Transfer learning, you learn it here, and you transfer it there. But question, have you ever seen somebody solving the equation in this domain and transfer it to another domain, which is a circle? That's very difficult. In computer vision, people do that, but they don't ask for accuracy, the accuracy that we ask. There are other methods, online training, continual learning, and so on. So here in this paper, in machine intelligence, we try to answer that question. If I solve the series law on the top, on the square domain, and I transfer it to a target domain, which is a triangle, or if I do the elasticity equation from displacement U and V on single circle, can I have two circles or a square where I have singularity and so on? The answer is yes, but not with simple regression. Those people do transfer learning, it changes the parameter a little bit. We want to go to the third one, have a dynamical system and what's called a oscillator, the human reactive system. We train it at the limit cycle, and then we go through bifurcation to a stationary cost. But again, the regression alone will not do it. What you make it do is to add the loss function and get the shift between the conditional distribution between the targets and the source. There's some extra mathematically interesting math that goes with that. Couple more thoughts. Google came up with this paper in Science called Gato, and this Gato was able to do 600 different tasks. And the argument was, implicit argument, probably is that when you do multiple tasks, there's synergistic learning. You're learning from, so you don't pay the cost of 600 times the task of one. The Google, they published in Science, we were interested to solve different equations using the neural operators on different domains. And indeed, it turns out that you can learn that. You have seen some work from other people on foundation models, neural operators, some variables for foundational models, where you also change the domain. I think Mishra and some other people in Europe solve nice 2D equations in nice periodic domains, but all the interesting stuff were intersecting basic come from the boundary. I'll skip that. I was interested in visual transformers, and I went to study with my collaborator from Proper from IBM, fruit flies. Well, fruit flies have only 25,000 neurons. Anyone knows how many neurons a human has? 86 billion. 86 billion. A fruit fly has only 25,000 neurons. They can smell, they can fly like crazy. They do lots of operations. So So it turns out that if you study them, there's a little fundamentally transformers, in fact, visual transformers. So my application was, again, I didn't just want to use it, I want to use it for my lab, and I wanted to see if the front line and learn solve PDs, because then I will find a role in that. The answer is not quite, but again, you can take a vision transformer, but I couldn't. Fructose. But you can, if you look at the vision transformer, the vision transformer is a good the encoder can be used in a use type of all of you will not agree the use cycle. You can use the same thing with the convolution proxy encoder. Will be my branch in the left part of you, and then the vision transformer is right at the bottom here. We call it Beetle, great in Beetle before. Thank for this. And then the output side of it. So this side of being a really good operator. So you can solve that's from so very, very coarse resolutions. You can get people that you can know all of that wavelet transforms and so on. And you produce models which are very small. And the last slide here is talk about a paper we did recently, whether we compare is really safer in China that did that strong. The question is, you have to learn all that stuff or actually put on and think I already know. So we have a paper published. And we set up various tasks, scientific computing tasks, what we teach in the classroom, and also scientific machine learning tasks. For example, we asked them to doing integration using neural operator. The one that they have the reasoning layers, they actually did a good job. They set it up like a mathematician, the right space, not just one type of function. Standard ChatGPT failed, and if you're interested, you can find this. If you're interested in what I said, there's a course that we developed for NVIDIA. It's on the NVIDIA website. It's called Deep Learning for Scientists and Engineers. And we teach all the frameworks, including JAX, and more recently we work with MathWorks, and we have the MATLAB machine learning framework now is equivalent to Plancker in terms of speed. And for you can the PD library there can be very useful. What our PDs and operators, and module 3, some values are on NVIDIA, in the library we have, and we downloaded one behind. Tomorrow, which is the library of NVIDIA. And then all kind of course stories that they were sent to us from around the world, depending on exactly to design a course. It depends on mathematics or science and so on. That I would like to thank you very much for taking the time to do that.
Thank you, George, for this very inspiring talk. I think that is a question in the audience.
I have a question about when you solve the HVD with school, do you need data there? Which data do you get?
No, this is the whole. Sorry, this was for middle forward, but not data.
Not data.
No data at all. This, things can be used in any fashion, right? Via the overspinner or the totally inverse or hybrid. No data, just about this.
But how do you check the accuracy of your solution from in that image?
I have the exact solution. The exact solution with for an LSQ control. The standard solution view. Not non-trivial solution, not set out.
But the first for fixing fish out, question about how you what was this that they having published might think had to the issue. And yes, might be high skills. So what was the resolution next generation of the institute based on history of the years of budget item is when we think about that. Yeah, it's like we have published a paper about the might think high movements.
Oh, the money thing.
Yeah. Oh, okay. Is the next generation?
Thank you. So there's a paper where we, instead of one head, we use phantom heads that we on the basis. So the reason we did that is because we can compute distribution very accurately. What I've said is this is not a next generation. This is really an application of pins to specific, just to quantify and get them. I don't know the next generation. I think the neural operators is the next generation, and how we can reduce the training of neural connectivity. So, the work in real time, the force offline is sort of like.
The question, but I made one. So when you said that you try this test with the 10% of the data with others. So if you take all the data, what would be the improvement? What would be the loss in terms of accuracy, of time of finding, in terms of time of getting the solution?
Yeah, so these are noisy data. So take all the data, the error was about 30%. 30%. Ours was very small, 1%, only 10% of the data, because you don't build in the propagation of sound and so on. So that's why I knew it sort of in advance. That's why I had done my homework. That's why I can.
Okay,
but
so by using more data, you would.
Well, they give you a video. They give you a video, and that's all you have. You don't have other producers. You don't have anything else. So it had to be data-driven. But because you see, you have the night wave, right, and then you have this refraction. So that gives a lot of local minima in the loss function. So they were not able to minimize them. The physics itself acts as a regularizer. So, for example, when I do pins, I don't use the weight decay regularization. I don't do L2 or L1 decay. I don't do the extra regularization because the physics itself is the regularizer. You have some data, then the physics acts as a regularizer, which is much better than arbitrarily saying that the weights are around zero. So my advice wasn't. So it drives it to the right, to the return.
Right, thank you for the addition. So you mentioned both the teams who had like relying on having such low, which felt the need of metadata, and it's the normal right nodes who don't need it, but very good job. Is there a reason for a system where we have like clear intuition on the load, but let's take that rule and should make something very good.
So in pins, you may or may not need data, and also in neural operators, if you know the governing equation, you can use physics informed laws. During training, you can use it. But overall, for faster training, it turns out that it's good to have some data. So even if you know the equation, it's better to run some simulation. Let's say a problem with it, I can give you numbers. We're looking at crack propagation in material. Okay? So you use, let's say, 150 simulations. It's only data driven, provide learning. But if you use the physics, you only need 10 simulations, and you get better accuracy because you have to learn the operator that don't follow. If you add other principles like symmetry or ontonicity and so on, in the loss function during training, you can even learn faster or right. So it's a balance. But there is a paper by my former student in science and advances called Physics Informed that uses physics. And we argue that we both get boundaries. Our experience is that even if you know the equation, it's better to have a few points because you can actually optimize it while optimizing.
No more questions? So I think we can close the session. Thank you again.